All right, this month we have Tom Bridgman. Bridgman.
Yes, that's you.
Thank you, Tom. Anyway, Tom is he works in the scientific visualization studio at Goddard, and he's been at Goddard for like 30 years now. But yeah, Tom got his PhD in physics and astronomy at Clemson. Then he joined the Compton Observatory Science Support Center at Goddard because he was working in gamma ray topics at Clemson. Well, unfortunately the budget caught him and he ended up moving over to SVS, and since that time he's been producing some of these visuals that you've seen on the NASA website and other places. So the real question is, how do you visualize invisible things such as electromagnetic fields or extremely tiny particles in a plasma? How do you visualize those things? And that's Tom's job.
The other thing about so anyway, yeah, I'm with the visualization studio at NASA Goddard Space Flight Center. I started there in, in 1999 when the budget for gamma ray stuff was dropping for the projects I was working on. And it was kind of funny because when I was in grad school, and I was trying to learn about gamma rays, I was doing gamma ray transport codes, and I'd always heard that there were these tools that computer animators use about, when they had to make a picture of something that was not real and render it in a computer. There were programs called renderers that did this kind of stuff, and so I actually started researching that. I found a computer graphics book about how to write the codes for doing this kind of stuff, and then I'll apply this for doing my gamma ray transport. Little did I know at the time that I would, in a few years, I would be working with this exact same type of stuff, but actually making imagery. So, let me first talk a little bit about the SVS in general. We have a number of different audiences that we talk. That we serve. Schools and formal education, we do a lot of products that we try to generate in a more general form. Educators have used our material. Informal education, that's usually lots of stuff for the, supporting press releases and things like that. Researchers, they get a new result for a mission. They want to be able to show the taxpayers what they've done, what their money has purchased. And for the general media stuff, which a lot of a bunch of people sharing their eclipse pictures here, like, yeah, this was a big event for Goddard and the Heliophysics division. So those are sort of our target audiences. One thing, a distinction I want to be able to make is what we mean by data visualization. And namely, the data visualization is driven by data. You've got a data source somewhere that you are using to represent it. You may include animation components. For example, if you've got something where it's showing cloud data around the Earth, well, you might want to have a nice looking Earth underneath that. So that might be an animation component that you use for that. But the data is sort of like the star of the show. And it's the thing you want to emphasize. Animation is used more for presenting conceptual ideas. You don't necessarily have an accurate model to represent what you're doing, so you animate. The atoms are big, huge things and stuff like that. And they got labels on them that tell you what they actually are, things like that. But you might actually incorporate some data in this. So we actually do a little bit of both. I mean, my stuff. Because so much of my stuff's invisible, I have to go and make use of it a little bit more. So one of the things our group works to do is to provide visualizations with some context. Like what I was saying, you might want to show Earth data showing clouds, and you want to show an Earth underneath. show what where it's day and where it's night. So sometimes you can see these patterns in the way the clouds move. So you want to be able to tell a story for that. You want the pieces to hold together. When people look at it, you can explain it, or sometimes if it's really nicely done or much more simpler organization, sometimes it's easy to, people just sort of like are drawn into it. They can understand it just by looking at it. You know, the whole picture is worth 1,000 words type thing. Very often we work with multiple data sets to show the interrelationships between different types of data. One data set might be driving some other event, and you want to be able to show those connections as best you can. Very often we're dealing with time series, data that are taken at various times, and we're stringing them together. We might have, for example, one of the missions I work with is Solar Dynamics Observatory. Every 12 seconds, it has an ultraviolet imager that takes a picture of the sun, full disk, every 12 seconds, and it's got, let's see, I think it's about 7 or 8 filters on there that take it, and they're kind of staggered a little bit, but sometimes you put that stuff together. It's kind of fun. In fact, I got one of my favorites. It's one of those types of things. We very often make use of camera motions and change of focus. You want to be able to show someone, you want to be able to zoom in on a place on the earth you want to talk about, but maybe you want to show the whole earth in the opening so people can say, okay, this is somewhere on the earth, and then you zoom in. So you might want to be able to emphasize that as part of the opening for your story so people get an idea of just what you're talking about. And of course, one of the nice things about some of the more realistic rendering systems is you get kind of a you are there feel. You can't get there actually physically, but you can make something that looks like you're actually there. You know, it's like you're driving your spaceship by the earth. You look out and there it is. So those are all kind of fun, and you assemble that stuff together to try and tell a coherent story, and as accurately as possible with the data you have. The SVS works with a bunch of different types of data. Unfortunately, I realized this morning that I didn't have an astrophysics one. We do occasionally do astrophysics. A lot of our stuff is focused on earth science, and that's sort of like some of the largest projects we get. And a large part, when I started the studio, that was sort of like the big thing that we did. We also had Earth atmospheric sciences down here. By the way, this is our website for if anyone wants to look at our stuff. There's also planetary we've done a lot of. When I first started the studio, I think it was Mars Global Surveyor had their MOLA instrument, had some of the first altimetry maps of Mars, where we actually built sort of like a 3D model of the planet, which was kind of a challenge for the computers of that back in the early 2000s, because they didn't quite have enough memory for some of it, so that created some different solutions. I work in areas where I deal from, it's the heliophysics division, but it really covers a lot broader range than that. We cover not just the sun, but the plasma environment around the Earth. So my joke is that if it's the ionosphere or above, it is my domain. So talking about what you could do if you went to our site, and a lot of people use our site for doing class lectures and stuff like that. We've got a lot of stuff that we try to do in general to make it so that others can use it. We, earth science, heliophysics, planetary science, astrophysics, all of our content is freely available, so anyone can use it. Educators use it. We like when you credit it, but it's not really required. We do have credit information for the studio on most of our pages. Our website, by the way, has a web page corresponding to virtually every animation we've ever generated. There's some of the older ones that we don't quite, have online because they were done with older technology that we weren't able to convert, but a lot of it is freely available online back into the 1990s. Speaking of the 1990s, the older stuff is in standard def video, which is much lower resolution than what we can do today, and is, not even what we call square pixels. So there's issues where sometimes, the Earth doesn't quite look round. But, eventually, we migrated to 720H high definition formats. So a lot of our stuff starting around the early 2000s started being rendered in that format. And today, most of the stuff is in either HD 1080, that's the higher end HD content, or even 4K. So, you can put this on a lot of high resolution displays and it's going to look pretty darn good. Not only do we have movies in various formats, and at one time we actually used to do, what was it, Windows Media format. I don't think that's supported anymore. But we provide movies and individual frames for each animation. So you get the highest quality image that gets encoded into the movie. But if you want to do something where you want to be able to say, oh, there's an interesting thing there, and I want to composite an arrow or something like that, pointing out something, you can do it with the original content and get a very high quality product afterwards. So, a lot of people read them. There are a lot of YouTube amateur music videos that use our content played, although they usually just use the straight movie on there. And our web pages, they have a download option for downloading this content. And, like I said, we like it to get credits, and we get specific credits are available on a lot of the animations. There's a handful that are actually a little bit different because of various other organizations that work with us for getting the data. So, how do we do this stuff? Well, some of the stuff I do, it actually makes use of some of the standard tools that were used in the regular data analysis. SDO imagery now it's 4K by 4K, so it's already ready for high definition stuff. But the other content that we generate, the images, I might process them through a standard coded process. But other things, we have to build a scene. And we actually use a lot of the tools that people that do computer graphics in modern movies use. Here's some screenshots from some of the tools that we've used. This one here I think this was one of my attempts to do some Aurora microprocessors in there where I got like some atoms, and I think that's a photon zipping off of it that I was trying to do to make an animation of an atom getting excited and then emitting a photon. This is in a tool called Houdini, so we got these fancy graphical user interfaces that there's parts of it that has, this is the objects there. These are some of the things you want to do and how you want to color them. There's some code you can put in there to make the things move in certain ways. There's another program that's free and open source called Blender, which I played with a little bit. It's good for if you want to get started into computer graphics. It's a fun tool to play with. And a lot of amateur animators start out with a tool like this. The downside is these tools are all very complex and every one of them is different. You learn the tricks on one, and they not all, some of the terminology may transport over, but some of it will not. But, so these are the kinds of tools that we use. And of course we have to use programming languages very often to take the data from the format the scientist provides it in and put it into something the computer graphics program can render it in. That said, my workflow is a little bit weirder than that because it turns out that RenderMan, which is a package written by Pixar Animation Studios that did films like Up and like Toy Story and that whole series of stories, actually is kind of a language. And you can actually, one of the things I got used to doing, because I had to deal with things that had really large scales, that the precision of a computer or these graphical windows couldn't support very well. I had to write stuff where I could take the simulation program and say, I want to draw a sphere here. I want to draw a plane here. I want to draw a curve that connects, from here to here. And I could write that in code, and that worked out very well for a lot of stuff that I do. So anyway, those are the kinds of tools that we make use of to generate a lot of our products. And if anyone wants to ask any question, I'm realizing I'm going fast. expected here. If anyone has any questions, let me pause here and open the floor if anyone has a question. Or have I just, was I that obvious? Okay, yes.
The Hyperwall was part of this visualization studio, wasn't it?
Mm-hmm. Yes.
Now, who do you contact now for a tour of that? I always found that was a very nice stop.
Yeah, I am not sure who the actual contact person is anymore. Mark Superau is the director of the SDS now. And so he would be, probably if you go to the SDS website, he's listed on the, on the bottom there as the appropriate official contact. And you could contact him and find out what's available.
Okay. Is Mary Perkins still there?
You mean Lori Perkins?
Lori.
No, she moved on. We were, yeah, it was like hemorrhaging brain cells when we lost her. She's still on Goddard, but we occasionally go over it and give her a hard time.
Okay.
Yeah.
Okay.
Yeah. So,
Was
there another question?
No, that was what I was going to say. I was going to ask you if Lori was.
Yeah. She still visits us on occasion, but yeah, we do miss her because she was always fun. So anyway, one of the things we keep running into is because we're bringing data sets together, sometimes the data sets that we get were all collected by the same spacecraft. So you would think that, yes, they always have to work together. But sometimes we're combining data from different spacecraft. They might have a different time clock that's offset a little bit from what you're expecting. The pointing direction may be a little bit different. I had a lot of that challenge when I first started with solar imagery. There was Trace and Soho, and there was a little bit of an offset between them you had to account for whenever you brought the images together. But little things like that you have to learn to manage. So data and image co-registration is always something of a challenge. And that's in the spatial domain. In the time domain, we also have the challenge of trying to make sure our clocks are all synced up in different time systems. For a lot of the stuff, for folks that are doing earth science, it's kind of straightforward. They're almost always close to the Earth. They might zoom in close to a ridge or something like that. And so they don't encounter this problem that much. But I've got some visuals where I start for Earth orbit and move out to where you can see the Voyager spacecraft outside the heliopause. And that actually creates some challenges for these types of programs in terms of, most of them are written to single floating point precision as opposed to double precision, which you really need for that. All kinds of other little things. You almost always find that these programs are made for computer graphics people that are doing stuff that you don't normally have to physically interact with. And so as a result, there's all kinds of little shortcuts they've taken that every once in a while you encounter. And that's another matter. We've got large volumetric data sets or huge amounts of data. You have a volume you might be talking about just a thin layer of the Earth's atmosphere around the Earth, and that's a pretty hefty scale because you want to be able to have it really, really small samples all around the globe. But we've got other sets where you have a complete volume, and there's even, the number of points goes up into the millions and even billions to try to handle it. So some of the software, we run into challenges importing data. Views and camera motions, you want to be able to fly around the little world that you've built inside the computer. So sometimes those get a little bit tricky. One of the nice things, though, for this stuff is we have what we call a render farm. And that is basically a bunch of machines, most of ours are running Linux, that work together. You can send, movie making is what is called a highly parallelizable process. You take a sort of a snapshot in a regular movie. It's an image, followed by another image, followed by another image. You can render each one of those images of that frame of a movie in a separate computer, and then put them all together at the end. And so we make use of multi-processing quite a bit. Yeah.
Is 3D rendering feasible for think it's feasible to use data. Imagery and 3D.
Oh yeah, that's what we're doing. I mean, that's,
So,
yeah, a lot. I mean, like I said, we're using a lot of the standard tools that are available commercially. There are a few scientifically specialized rendering tools that, yeah, that we haven't really. Actually, I want to play with that. I just got to find the time to do it. But yeah, I mean, so yeah, we pull these data sets into one of these programs very often and build a scene, move the camera around, and then render it. Sometimes they might just want a still image, but very often we're rendering whole movies and that tell stories. Yeah.
Color scales are always a problem. How do you manage color scales?
That we have to play it by ear. You put one together, and sometimes they work, sometimes they don't. In fact, that's one of the heftiest arguments we have sometimes, especially with the scientists. They say, I published my paper with that color bar. So, well, you want to put that color bar on a data set that's over the earth, so the blue end of your color scale isn't going to show up. So, you know, there's things like that. That in fact, the meeting we had today, there was a challenge with that. Yes.
You do a dynamic range adjustment too on the data before you use it?
Oh yeah, I mean, these programs will let you choose the scale, and you might want to say, oh wait, well, one astronomical unit corresponds to 1 unit in a renderer. I run into the issue that it turns out it's Earth rate. If we're close to the Earth, we'll have an Earth radius of 1. And then if I want to move out to out beyond the Earth's orbit, I've got to multiply that by about 22,000 to move out. So, you know, and we actually have, some of these renderers actually support the trick of, okay, if I'm close to this thing here and I want to call it 1, if I move out here, I can switch to a different scale, and all the stuff that I build there is on this different scale. And sometimes that gets us around some of the problems. And we've used that numerous times. One of the nice things about some of the tools that are available now, there are so many people doing interactive stuff. There's a package called OpenSpace, which actually can take you from close to the Earth to out to the edge of the observable universe with the Sloan Digital Sky Survey in very simple moves. It has a way to rescale as you move. And so they do that on the fly. And it's really quite impressive. But yeah, the computer graphics, I mean, between the graphics cards that are available, some as standard products in small, home computers nowadays. I mean, gamers are the ones that help develop this stuff. That was another thing that I was playing with a lot when I first started with the studio was computer games and working with computer graphics cards. But yeah.
So do you run into computation difficulties, or is it just what the commercial cards, graphics cards can do? I'm just curious.
Well, there's all kinds of things that qualify as computation. Sometimes it's just that it takes a long time. There's some processes we got running right now where something might have a wide view, and you'll see that, oh yeah, that renders a frame every 10 seconds. And then when you get close and you're seeing more detail and stuff like that, all of a sudden it's going up to taking 30 minutes to render a single frame. So there's stuff like that. Some of it is just, you almost got to do brute force. That's another advantage of having multiple machines that you can spread the stuff out on and use for, split the job up. So, sometimes you might have a bunch of frames that all get rendered and generated and are spit out, and then there's that handful of close-ups that you got that you're still waiting for. So yeah, there's little bottlenecks like that, and sometimes we find that if it's one of those things where if you're running that process a lot, it might be worth trying to really gnaw through the details of that problem and find a better solution. But if you're running it once or twice for some drafts and then a final, you don't worry about it too much. It's something you say, okay, launch it on Friday and it'll be done by Monday.
Did you bring any examples of your Heliosphere?
Oh yeah, I got movies. I brought movies. Lately, we got with our new director, Horace Mitchell. Ran the studio for a lot of my time there. A few years ago, he retired and we got a new director and we started doing some other new interesting things. Unfortunately, I that knowledgeable on this in this particular area for this stuff, but it's neat stuff that they're doing. And some of the stuff some of you might have seen from the eclipse. One guy, they put together an interactive game for kids on snapping a photograph of an object, just passing in front of the sun. My grandchildren helped test it at one point when they were looking for kids to test it. I tossed it their way. And so there's things like that. It's over on one of the kids' sites for NASA. And I've tinkered with it a little bit, haven't with it. The thing that really got a lot of play was the interactive eclipse map. We actually had to host this thing on a larger shared server because they would have brought our file system to its knees if the number of people that were hitting this thing actually got on there as the eclipse approached. And you can see the hits. I mean, they were slowly increasing, and then a few days before they just skyrocket, and then the next day it's down. It just falls off. But yeah, they made an interactive eclipse map. You could click on the location, and it would show you the starting time of the eclipse, the ending time of the eclipse, what percentage it would cover, things like that. It was a really cool tool. I played with it a lot because we were looking at everyone. Anytime they would say, "Yeah, I'm going to so and so. Let's see what's going to be going on there." So yeah, these are some of the newer things we're doing, playing with interactives and stuff like that. Another big thing that the studio has done recently down at NASA headquarters is the Earth Information Center. This is a big display. I mean, someone mentioned the hyperwall earlier. This is like I actually have not yet seen the whole thing in place, but I think it's about almost the width, like between that door and that door. It's a bunch of little displays stuck together, synced up, so they can display large images of Earth data in near real time. We have processes running on our systems, and they will take satellite observations and combine them together. You can see some of it's even got the gaps there for the satellite tracks of different Earth science data sets. And this is a very in-depth site. There's a web version of it that you can go to and see a lot of the content that's playing down there. You can go into the lobby at NASA headquarters where they got this thing on a big wall. There's actually at least two others that I know that are being built. One is at the American Museum of Natural History downtown and at Kennedy Space Center. So this thing is quite impressive. And if you go to the SDS site, and there's some pictures of it in the lobby from NASA headquarters. Oh, whoops. Oh. Oh. Got loose. Oops. Okay, well, you can fix that. Thank you for bringing that to my attention. Okay. So, missed it by that much. And there's challenges that we'll be dealing with a lot in the future. One of the ones that always interests me is keeping ahead of what the scientists can do on their desktop. Computer graphics cards have gotten faster, better, nicer quality, stuff like that. There's more stuff they can do near real time. There's loads of scientific applications that have made use of this capability. You can bring in volumetric data sets, run it on your desktop, do all kinds of spinning around it, examining. Sometimes bringing in extra data components to use it for actual analysis and data visualization. So, in the interactive case, when you want to be able to, look at it on your desktop machine and spin it around and stuff like that, we call that interactive. A lot of the stuff that we do is deferred rendering. One of the things that I like to distinguish on that, there are all, as we said, there's problems that are really compute intensive. And if you've got a really big data set, sometimes it takes a long time to do that. So that will for a long time, always be our domain. But as computers get faster, that domain is moving to higher and higher density data sets. So that's one of the advantages of doing this stuff in what is called a deferred mode. You have to nail down your camera motions and say, okay, I'm going here, I'm going there, and it's fixed. But if you're not trying to give someone immediate feedback on their computer, it can work out pretty well. We do use commercial rendering software mostly. Like I said, the Houdini is one of the tools we're using very heavily. But one of the challenges there is scientific users are not their primary customers. Their customers are the big movie studios. They're doing, animated feature films and stuff like that. So we've been very fortunate. Pixar has been very receptive when they make some change that breaks something that we relied on. We can say, can you fix this or find a new solution for it? And they are usually willing to work with it. I think they like being able to say, next, it uses our stuff. So, while we're in that sweet spot, we're going to take advantage of that. And they've been very willing to work with us. And of course, more recently, there's what we call the rise of the physics-based renderers. They are actually starting to do actual photon radiation transport in these rendering systems. It used to be, it was sort of like, oh, you had a light here, you had an object here. The thing would compute the distance to that object to determine how intense the light would be and what it would reflect at, whereas now it actually steps the photon through. It does some other tricks to make it run a little bit faster. But, one of the challenges that I had when I first started doing this stuff is in astronomy you talk about opacity, and that's something that's a nice, continuous functions in determining how transparent something is. Some computer graphics programs, one of them use transparency, which I guess is 1 minus the opacity, and then the other one used the opacity defined slightly differently. And so it's a little bit challenging sometimes. You got to keep in mind those different notations and how they use the terms, which is one of the first things that you start dealing with when you're trying to translate what the scientist is telling you to what the computer graphics package is expected. So anyway, so those are some of the challenges that we look towards in the future. Unfortunately, this picture is old. There's a few people that have left. Someone mentioned Lori. There she is back at that time. Mark Subarow is one of our new director. AJ works remotely. There's Horace. But yeah, it's been a great group to work with. And it's nice that we're all help each other when we run into problems on using the tools, because these are complicated tools. You got one dialog box and it's got 5 tabs in it. There's 40 settings in each one. It's like, I can't get this to render right. Oh, you got to go to this tab here and go down there, and So it's always kind of tricky. But anyway, that is the end of that. And if anyone has any questions right now, one thing I will do is I will put on. I've got a list of movies that. I can just start playing here. This is one that one of our new guys, AJ, did. Basically, it's sort of like a taxonomy of different binary black hole star systems. The accretion disk, the primary star, various different systems. Let's see. I think I studied that one in Cygnus X1 was the one that I did my dissertation on. GX339 -4. There's one that was discovered by GRAA right there, J1655. So this is one of the samples that we've done, and feel free to ask questions. Don't let me prattle on here. Oops. Wait on. Which is the step into the next one? Sticker. Just a minute. Yeah, there's a problem playing video on this thing. It's if you get yeah. So here's another one. Mark Subarow did one of these here. This is pulsars in the galaxy. He starts out with a 2D projection of where they are in the sky, and then pulls out, I believe this is Gaia data that he's got in here. Showing us, and the different icons there show you which type of pulsar it is. But this was a fascinating, and then it pulls out the top-down view of the galaxy and where they are. So that's very nice.
What galaxy is that?
That's our galaxy. Yeah, it's our local, yeah. This was a very elaborately done piece. Took quite a while to work out some of the challenges in it. Okay, I think there's actually audio for this, but I'm not hearing it right now. But showing the clouds around the Earth, and then showing these atmospheric rivers that form. I think there's one hit in California, or hit one either just recently or is about to hit. In the area, but we got like, and you see there's some of the spots where I think we actually plot like where snow is falling. Is that? All our little securities. Well, the problem is I can't see the mouse where it is, so I get too close to the edge there. But yeah, there's a lot of. Okay, yeah. Here's further on.
Back away, please.
Sure. Where you see the system pulling over and pulling all this water from the Pacific and dumping a lot of it both as precipitation in some form, rain or snow, on the western, western North America, part of North America. And so we got arrows there showing the flow of the air, I think that's the water vapor density, the high pressure region and stuff like that. This one took quite a while. They were doing a lot of feedback, working with the scientists to try to get this to look this really, really nice. And it was really impressive to watch because, man, there were some early versions that were like, oh boy, this is going to be tough. But they pulled it together. It was great. This is a fleet of Earth observing satellites. Oh, okay, yeah, it's fairly recent too. March 7th was when this one was generated. So these are, some of them are familiar, Landsat. A lot of stuff has changed since I first started with the studio there. Landsat, of course, always. But yeah, that's the kind of the Earth observing fleet there. And I think this is one of the ones that is part of the Earth Information Center, and they update this thing daily. So if you go down and look at the Earth Information Center, it's like, oh, this was another very complicated one showing the sort of CO2 budget. Another one that you're trying to explain a really complex thing and with a bunch of different data sets, and unfortunately some of this stuff breaks down at this resolution. But showing how I think that's the CO2 budget, what's absorbing, what's emitting, and stuff like that. But this one was very cool to watch it in development and see the different views that we're showing. And the splashing here, I believe, is the diurnal cycle. You're seeing impact of day and night on the uptake probably of CO2 by plants and such. But yeah, so they pulled these pieces together to try to make it explanatory. There are some of the stuff, you put this stuff on a big hyperwall and you just sit there and watch it. It just really captures your attention. Oh, this is one of mine. Back when New Horizons was flying by Pluto, the CCMC, that's the Community Coordinated Modeling Center, or Coordinated Community Modeling Center. I always get those two mixed up. Doing space weather. We've got outflows from the sun. The sun, because of its magnetic field, generates sort of these ripples in the solar wind from the magnetic field that create this spiral pattern that moves outward from the Earth. And so they did this big model run that you're supposed to sort of like, can you predict the space weather at Pluto when New Horizons gets there? And so we did this run there. This also used a technique that I had experimented with, where I used a different color. Like red is the temperature of the plasma, blue is sort of like the density, and and green was I think green was the density as I think about it. This is one of the ones that I did originally as something else, and then I sort of fell in love with it because this is the most artistic thing I've ever done. That's what I regard. SDO has all these imagers that take different pictures of the sun at a high cadence in ultraviolet wavelengths. And originally I was trying to find out how much of a difference there was between the edge of the visible surface of the sun and what you see in ultraviolet light, because that's what it's called, that layer is called the chromosphere. And we were getting ready to launch a mission that was going to study that. So I said, oh, wouldn't it be great if I could get a quote, picture of the chromosphere? So I had to find a way to present all these images together, properly overlaid and code registered, so you could see that difference. It turns out that difference is only about 8 pixels. Couldn't really do anything. But this thing became one of my favorite images. It shows why we look at the sun in different wavelengths. We've got, okay, well, I'll stop recording it, but don't come back to that. You can see how the similar features change from one filter to the next. Some things that are bright in one filter are dark in another. Some things you can see the coronal loops that are plasma flowing along the magnetic fields. And watch the sunspot as it comes through here. There's a little thing that looks like a little arc going on right in there as the sunspot passes in. Then you see the loops and the plasma motion in the different filters and stuff. And yeah, I want to try to find a time to write a tool that will do this for any range of time that you want to do for SDO. But yeah, so yeah, that's one of my favorites. This is what I was talking about before, showing the missions that are observing the heliophysics fleet. Yellow missions are satellites that observe the sun. Green observe the local Earth magnetic field. Yep, ACE. Yep, we're out here at L1 now. SOHO, wind, still operating. And then we pull out from the Earth. And this is a real challenge for those regular standard computer rangers. Got Parker Solar Probe in there, Solar Orbiter in there. Stereo A is still operating. It actually passed by the Earth just recently, 6 months ago, I think. And then finally I pull out, and you can see part of the trail right there of the Voyagers, which are the ones that are out furthest right now. And I'm told at some point we may get New Horizons maybe transitioned over to Helios. So the next time I generate one of these, I'll have to put New Horizons in here. But we see these things sitting out. This is a change in scale of about 10 million. So a little bit tricky. This was an interesting exercise we did with the Swedish solar telescope in the Canary Islands. Let me go back to that. With the Swedish solar telescope, they had this very high resolution telescope that looks at the sun. And we thought, well, wouldn't it be cool if, actually some of the producers with the Helio division said they've gotten a poster that showed this and said, we think it would be really cool if you could put something together with this data. So we contacted the guys, and they sent us one of their nicer data. These are ground-based imagery, by the way. It's taken from the ground. With a nice little sunspot there, you can see the convection cells. There's a little bit of ripples that you see every once in a while due to the turbulence in the Earth's atmosphere. But this one's also it really looks good on a hyperball too. This is one of the more impressive ones there. And I think this. And here's another one where we did far away, where we were showing how we got Parker Solar Probe, Solar Orbiter, Stereo A, and SOHO sitting here. And when they were launched, and a lot of people realized that, oh, at various times they're going to be lined up so they could sort of like help reinforce each other's information. So you saw there was a little purple thing there. That was whenever two missions were lined up on the same magnetic field line from the sun, so you could measure something that was both near the sun and further away from in that same flow. There's some of them here where I've got the imagers coming on, and you can see like here, Stereo A sees the sun, Solar Orbiter sees it, Parker sees over there, but some of them are actually in the locations and they can actually do a measurement. So that was one of the things. And so we actually itemized a bunch of those to make sure that we could catch and do stories about them. But yeah, really cool set of missions to work coordinated together. It's great when you can get a bunch of them to get to work in different areas. And I think, this was something I did for a new mission which actually recently died, called ICON, that was looking at the upper atmosphere and the plasma environment there. And we got, here's another one with multiple data sets. We've got the model of the ionosphere. You can see how the ionization grows as the day moves on. And you can also see, we also put in wind patterns in there too that were from a horizontal wind model that is done for the upper atmosphere. And ICON flies around and does measurements of this. So that one I was also particularly proud of because I pulled things together in a way and they actually made sense. And I thought that was the last one, but and unfortunately this one doesn't have audio. The audio is not here. Let's see. What's a speaker? This is one of my coworkers that works with the LRO imagery. Oh, there it is. This is one of my favorite things I end my Hyperworld shows with, because I think it's so beautifully done. Prior to this, they didn't know who took that picture. Can you hear it? No. What is it? Okay. Well, I need to fix that.
Navigator Jim Lovell was in the
That's
equipment bay about to make sightings on lunar landmarks with the onboard.
And this is also freely available on the SGS site, by the way.
Observing the moon through his side window and taking pictures with a Hasselblad still camera fitted with a 250mm.
Phil Andrews actually came to the studio and talked with us about this.
It was mounted in Gordon's front-facing window, the so-called rendezvous window, photographing the moon on an automatic timer, a new picture every 20 seconds. These photographs, matched with LRO's high-resolution terrain maps, showed that Gordon was still turning Apollo 8 when the Earth appeared.
Very distinct all this stuff up with LRO there. It was really cool about this
Apollo 8's 3 previous orbits that was unseen by the astronauts now came into view in Bill Anders' side window. Here's what it looked like, as recreated from LRO data by Goddard's Scientific Visualization Studio. You'll hear the astronauts' voices as captured by Apollo 8's onboard tape recorder, beginning with Fred Brown announcing the start of the roll maneuver. And you'll see the rising Earth move from one window to another as Apollo 8 turns.
All right, roll. Ready? Set. The impact crater was at just by the subsolar point on the south side and the floor of it. Here we see that there is one dark hole. But I couldn't get a quick enough look at it. See that it might be anything volcanic. Oh, yeah, I did a picture of it. Okay, I'll take that. I'm gentle. There, color film here.
Like big kids up there. I'll come up again, I think.
Seeing the Earthrise was an unexpected and electrifying experience.
Apparently there were several different versions of this image floating around, and were some of the different ones that they took.
20th century. In 2018, the International Astronomical Union commemorated the event by naming a 25-mile diameter crater Anders Earthrise. The smaller crater was given the name 8 Homeward. Both craters are visible in the iconic Earthrise photograph. I'm Andrew Jacob, author of A Man on the Moon.
So yeah, this is one of my favorites, just because the astronauts are like big kids up there and they're talking so excited. But yeah, and so that's freely available on our site. Also, this is like about the third version. So over the years, we found different information that we would integrate in and make a new version. So anyway, so that is pretty much all I got. I'm getting to get the impression that I may have kept you guys long, and I apologize for that. But yeah, any other questions or?
Any more questions?
So your studio that is made up of what, civil servants, DSP?
Yeah, we've got, there's several contracts that cover the people in our group. We got 2 regular full-time system administrators. And then a lot of us are animators. There's a few of us that actually have more of a science background, some more computer graphics. And it's really useful to have sometimes for translating what the science say. It really gets a challenge at times. But yeah, where are we at now in terms of people counting? Yeah, a bunch of people are now. We got a bunch of people working off-site, including out of state. Our meetings are getting pretty big.
Your house in Goddard?
Yeah. Yeah, we're building 28. We have the big supercomputers in the building, so our offices are always freezing cold.